Okay, welcome North Tahoe chemistry students here. I'm going to watch a brief video, take some notes on an introduction to thermochemical equations, and then we're going to practice the specifics and the more difficult aspects of them together in class. This just serves us to give us some background knowledge so we all have to move forward. Things we're going to need to do or to know before we go into this is what is a mole? How do you use the periodic table to determine the molar mass of a substance? And how do you interpret a balanced chemical equation? Do basic stoichiometry. The objectives of the lesson will be what's an exothermic and an endothermic reaction? What does an exothermic and endothermic reaction look like on an energy diagram? And how do we incorporate energy absorbed or released during a reaction into a chemical equation or create a thermochemical equation? So we'll get started with a brief review of what heat actually is. Heat we think of as a unique form of energy, but it's actually a transfer of energy, and it always occurs, according to the laws of thermodynamics, from a hot object to a cold object. Really remember what's happening. What makes something hot is that its particles, the atoms or the molecules that make it up, are moving rapidly. A cold object has particles that are moving slowly. So really what we're talking about is a transfer of motion from a hot, lot of motion substance into a cold or a lower motion substance. We do need to have a couple ideas here. We're going to define, if we have a transfer, we have to have two things to transfer from. So we're going to speak of a system, and in this diagram, the system would be whatever is inside of the flask. The surroundings would be the immediate surroundings of the flask. In this case, we're looking at the arrow around here, and then kind of a grand term, but all of those things, the system and the surroundings, are sometimes referred to as the universe. Everything could be defined as a system, and everything else is a surrounding. So some definitions that we've already actually seen before, exothermic and endothermic. Exothermic means that you're going to transfer heat from the systems to the surroundings. So heat goes to the outside in an exothermic reaction. Endothermic means the opposite. Heat is transferred, or energy is transferred from the surroundings into the system. For an exothermic reaction, that means if we lose heat, the system cools down while the surroundings warm up. We might say the reaction gives off or releases heat. The system, in an endothermic reaction, the system warms up and the surroundings cool down. We would say that the reaction absorbs heat. So we see these things, these types of reactions all of the time. Explosion or a combustion or the burning of a candle or wood would be an exothermic reaction. It's giving off heat. In some cases you can feel it if you're close enough. Less common are endothermic reactions. That might be a reaction like in an ice pack. You break something open inside of the pack and all of a sudden it gets colder. It gets colder because it's pulling heat in from the surroundings, so it feels cold to you. So in an exothermic reaction, the reactants involved, remember all chemistry is, if we take the reactants and we put them in there and they mix around together, boom, they become products. That's all real chemistry is at the beginning aspect. It's a reorganization of reactants into products. So when that happens, sometimes heat is released, and in an exothermic reaction, that's what happens. So in the process of turning the reactants into the products, we release heat doing that. So heat would leave in an exothermic reaction. In an endothermic reaction, the same thing happens in terms of the chemistry. It's just a reorganization from reactants. So we put reactants in there and they mix up. But we notice it won't actually proceed unless we add energy. So we'd actually have to put energy in there. That would come in from the surroundings. And we've got reactants and it's taking in heat. And boom, they become products. But this type of reaction took heat in from the outside. So heat, our variable Q, had to come in order for the reaction to proceed. That's an endothermic reaction. We'll often see these reactions portrayed on energy diagrams where on the y-axis we're looking at potential energy. That's the energy that's stored in the chemical bonds of the reactants and the products. And then on the x-axis, sometimes we just call it time, or we refer to it as the reaction progress. So what does it mean for an exothermic reaction to give off heat? That heat had to come from somewhere. So that means it started with a higher energy, a higher potential energy in the form of the reactants, and it ends with a lower potential energy. So the products are actually more stable. They have lower amount of energy. This difference in heat, right? We start at this level and we end at this level, so that's this arrow here. That's referred to as the enthalpy of the reaction. I don't know why they use that word. It just means energy. We gave off energy in the form of heat to the surroundings. For an endothermic reaction, what happens there is our reactants actually start at a lower energy. So the potential energy in the bonds of the reactants is lower than the potential energy of the bonds as products. So in this case, we end up with products that have a higher potential energy, an increase in enthalpy or an increase in energy for an endothermic reaction. So they can look really similar if you don't look close. Right? So an exothermic reaction, because it releases heat, it means that it's lost energy. So delta H will be a negative value. The final state will be lower than the initial state in terms of energy. For endothermic, it's the opposite. Delta H, the increase in energy, or enthalpy sometimes it's called, is a positive value. The final energy of the reactants is greater, of the products rather, is greater than the initial energy of the reactants. This little hump, you'll see that we have to have this hump. It's called activation energy, and we'll talk about that in more detail later. But essentially, you know that combustion, if you burn candle or you burn wood, it doesn't just happen naturally. You have to add a spark or add a match to it. That's the activation energy in order to get the reaction to proceed. We'll talk a little bit more about that in detail in the coming days. So again, how would we detect then an endothermic reaction? It may not always be obvious. Well, we know that we should have products that have more energy than the reactants. That means that energy had to go into the system from the surroundings. So that means if you are holding the flask, you are the surroundings. And if energy is going in there, it's leaving you. So if you're holding a flask with an endothermic reaction in it, it's going to feel cold to you because you're losing heat. It's gaining energy. It's actually warming up, but you're losing the heat. An exothermic reaction would feel the opposite. Its products have a lower energy. So that means that during the reaction, they've given off, or the system lost energy to the surroundings. So if you're holding a flask that has an exothermic reaction going on it, it's losing heat, getting colder, but that heat has to go somewhere. And if you're the surroundings, you feel that as warmth. So you feel warm when you're holding an exothermic reaction because it's giving off heat to you. You feel cold when you're holding an endothermic reaction because it's taking heat from you. So finally, how do we write this? How do we use energy in terms of a traditional chemical equation? Well, we just write in the energy, the heat absorbed or the heat released, as a reactant or a product. So an exothermic reaction, the heat will actually appear as a product because it appears as though it was produced with the products. So I'll give you an example here. So if we look at the formation of calcium hydroxide, right, this is a synthesis reaction. Calcium oxide plus water will yield calcium hydroxide. But this is exothermic. It also produces or releases a lot of heat. So oftentimes we'll write this equation, the thermochemical equation, which includes the energy, as the heat as a form, as a type of a product. So in this case, the heat released is 65.2 kilojoules. So it's written as a product. Sometimes you'll see it just written as a regular chemical equation without heat, and then afterwards they'll tell you the change in enthalpy or the change in energy. And remember, for an exothermic reaction, the products have less energy than the reactants, so it's negative. So we might just write it this way, the balanced equation plus decrease in energy. For an endothermic reaction, remember, it appears as though heat is really a reactant. It goes into the reaction and then produces the products. So sometimes we write those as heat as actually a reactant as the energy in. So an example might look like this. So in this reaction, we're looking at the decomposition of sodium bicarbonate. That's this, better known as baking soda. It's what makes our food, our bread, and cakes rise because it gives off carbon dioxide. But anyways, this is an endothermic reaction. It takes in heat to proceed. So we put, one way to write it is to put the amount of energy or the amount of heat that it takes in as 129 kilojoules in this case as a reactant. The other way to write it is just to write out the chemical equation here in this case, and then to the side we say that this was an increase, this results in an increase, a positive change in enthalpy of 129 kilojoules. Now why this is important is because now we can now read a thermochemical equation and read it like before. We can read it as a recipe to predict exactly how much energy we're going to be released or exactly how much energy is going to be absorbed. In this case, I would read it as 1 mole of calcium oxide combined with 1 mole of water will produce 1 mole of calcium hydroxide, and 65.2 kilojoules of energy will be released. We could look at this one down here, 2 moles of baking soda plus 129 kilojoules of energy will produce or yield 1 mole of sodium carbonate, 1 mole of water, and 1 mole of carbon dioxide. So we read this just like we did in our basic stoichiometry unit, where energy becomes part of our ingredients or part of our produced product in this case. Okay, so fill out the Google form with a few basic questions, come to class with notes, and we're going to work with these ideas in the future.